Let's go back the other way. Let's see how we can integrate our inverse trig. Well, let's start with the answers that we got yesterday. If I end up with an integral which is in that form, dx to the square root of a squared minus x squared, that of course was one of the quick ones, the x over a, so if I'm going back the other way, that must have been the inverse sine of x over a, plus of course a constant. Mind you, it could also have been minus the inverse cos. So your choice what you want to make it. It just means the constants would be different depending on which one you pick. And if it's the a squared plus x squared one, got to be careful for this one, because you'll actually end up with 1 over a. Because remember, when we differentiated that one, we ended up with a over a squared plus x squared. That's why, again, I tend to prefer looking at this way. I want to get it in the form of the derivative, the square root of a squared minus function x squared. Then I know it's the inverse sine of function x over a, or negative inverse cos. And so the derivative on a squared plus function x squared would be 1 on a inverse tan of function x on a, plus of course a constant. So dx on the square root of 4 minus x squared, that's in one of those standard forms. So I can look at that and go, oh, well, that's just the inverse sine of x on 2, plus a constant. Dx on 9 plus x squared, again, it's in that very simple form, but this is the one where I've got to remember 1 on a out the front as well. So a third inverse tan x on 3 plus a constant. Let's do a definite one. So dx on the square root of 2 minus x squared. Once again, it's in the very simple form. So I know that's inverse sine of x on root 2. These sort of numbers, again, crop up a lot because when I sub in, I end up with exact values. So inverse sine of 1 on root 2 minus inverse sine of 0, and we get pi on 4. And it is pi on 4, remember. It is not 45, because the calculus relies on this being in radians. And that's important now, because clearly pi on 4 is a different number to 45. When pi on 4 is 3.14, etc., 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 divided by 4. So if you're talking about an area under a curve, that's very different to having an area of 45. So differentiate, hence evaluate. The problem with this one is, because of the way I do it, how does it look like I didn't fudge it? Because I'm just going to go, oh, okay, that's all right. That's the derivative on the square root of 1 minus the function squared. Oh, so it kind of looks like I just fudged the answer, but I didn't. Because that's how I would have done it. Hence, evaluate. Well, therefore, if I differentiate inverse sine of e to the x, I get that. When I integrate that, I must get the inverse sine of e to the x. Going from minus log 2 to 0. So e to the power of 0, well, that's 1. E to the minus log 2. Remember, e to the log will cancel, so that minus needs to come into the log. So it's now the log of 2 to the power of minus 1. The e to the log will cancel. 2 to the minus 1, which is, of course, a half. So we have inverse sine of a half. So pi on 2 minus pi on 6, pi on 3. Here's one that's more interesting. So dx on the square root of 4 minus 9x squared. So I would like to create the derivative on top. But remember, it's not the derivative of 9x squared, because that's the function squared. So it's the derivative of 3x. So I'd like 3 on top. So 3, balance it out. I've got a third out the front. So that gives me inverse sine of the function over a in this case the square root of 4, which is 2. So I get a third inverse sine 3x on 2 plus a constant. Okay.